A very good morning to one and all. This is Anusha, lecturer in physics, working in general department at SS Government Polytechnic, Zahirabad. For first year, second sem students, I'm dealing with applied physics with the subject code 18 common 203F, and from our syllabus we are discussing the fifth chapter, that is electricity and measuring instrument. From this chapter, in today's class we are going to learn about combination of resistors in series and parallel. We are going to see the resistance of a resistors when they are connected in series and parallel. To understand this, we are using a small PowerPoint presentation. So let us move on to today's class. The main objective of today's class is, on completion of this period, you will be able to understand the resistance in a circuit when resistors are connected in series and parallel. So before moving on to today's class, let us recall what we studied in previous class. We have seen about specific resistance, conductance. So what is today's topic? That is combination of resistors in series connection. Here we can see three resistors R1, R2 and R3 which are connected in series. When we can say that the resistors are connected in series combination, that in a circuit, if the same current flows through all the resistors, then we can say that they are in series connection. So the effective resistance, combining all the three, we can equate it to Rs. Now we are going to find what is the value of Rs. So consider three resistors R1, R2. You can see here R1, R2. I'll show you. We can see here this is R1, this is R2 and this is R3. And combining all these three, we got Rs. So now the current I which flows through R1 and it enters to R2 and finally it reaches R3. In series connection, the current flows only through one path and it will be same. This is very important point to remember, that when resistors are connected in series, the current flows only through one path in the circuit and it will be same when passing through each resistor. So according to Ohm's law, the potential difference across R1 is, as we all know that Ohm's law is equals to IR. So here across R1 it is V1 equals to IR1, across R2 it is V2 equals to IR2, and the potential difference across R3 is V3 is equal to IR3. So here we can see that there are changes in voltages and resistance, but I is same. So we can take these three equations as 1, 2 and 3. Now the potential difference V across the series connection, it is V given by V1 plus V2 plus V3. So using equations 1, 2 and 3, we'll substitute what are V1, V2 and V3. So they are I R1 plus I R2 plus I R3. We can take I as common. So we'll get I into R1 plus R2 plus R3. So it is V by I is equals to, we are simplifying it. It is V by I is equal to R1 plus R2 plus R3. So it is equation 4. Now as shown in figure, in case of series connection, the equivalent resistance Rs is given by V by I. So V is nothing but it is the total potential difference in the circuit. That is, by combining V1, V2, V3, we got it as V. So we'll substitute Rs as R1 plus R2 plus R3 using equation 4. Using equation 4, R1 plus R2 plus R3 is equals to V by I. But here V by I is equals to Rs. So Rs is equals to R1 plus R2 plus R3. So what it tells us? It is the effective resistance when resistors are connected in series is given by the sum of all the resistances of resistors. So if we have n number of resistors in series combination, so the equivalent resistance Rs is given by the summation of all the resistances of resistors. So it is the single value of resistance which may replace the number of the resistors in the circuit without changing current and voltage in the network. So that is about the resistors connected in series. Now we'll move on to combination of resistors in parallel connection. Now here you can see R1, R2 and R3 which are connected in parallel connection. So the equivalent of these three is Rp. Now you can see in the diagram, when resistors are connected in parallel combination, the current across them is changing. The path of current flowing in the circuit is changing. So we got I1, I2 and I3 here. Whereas in the previous case, as the path along which the current is flowing in the circuit is same, so we got only one I. Now consider three resistors R1, R2 and R3 which are connected in series. Oh no, it is in parallel. The current I splits into 3 and flows through R1, R2 and R3. Now in parallel connection, the voltage remains the same. Therefore, the total current I equals to I1, I2 plus I3. Now let us see what is I1, I2 and I3. Now what we have seen, in parallel connection, voltage remains same. So the potential difference across R1 is V and across R2 is V and across R3 is V. So it is not V1, V2 and V3. It is V only, because when they are connected in parallel connection, the voltage drop across them is same. So it is given by I1 R1 across R1, I2 R2 is the potential difference across R2 and I3 R3 is potential difference across R3. So V I1 R1, I2 R2, I3 R3. Using this relation, I1 is given by V by R1, I2 is given by V by R2 and I3 is given by V by R3. So we have taken them as equation 2, 3 and 4. Now substituting 2, 3 and 4 in equation 1. So we have seen that I equals to I1 plus I2 plus I3. So that is V by R1 plus V by R2 plus V by R3. Now in this parallel combination, the equivalent resistance Rp is given by V by Rp is equals to I. Now substitute this in equation 5, we'll get V by Rp is equals to V by R1 plus V by R2 plus V by R3. We can take V common on right hand side, and when we simplify it, we'll get 1 by Rp is equals to 1 by R2 plus 1 by R2 R1 plus 1 by R2 plus 1 by R3. If there are n number of resistors in parallel, so it is so on up to 1 by Rn. So in a parallel connection, the total resistance of a circuit is determined by adding the reciprocal of the resistance of each individual resistance, and it is always less than the smallest resistor present in the circuit. As it is reciprocal, we'll get the value of it as very less. Now let us summarize it. We have discussed the following. We have seen the combination of resistors in series connection and parallel connection. So let us solve some questions here. Calculate the total resistance between the points A and B. You can see when I is traveling from A to B, at the middle of its, or else on the way, you can see 1 ohm and 2 ohm. Here the path of current is changing. So these two are connected in parallel. So first we'll find the resistance across 1 and 2, and then 4 ohm, 3 ohm and the result of 1 ohm and 2 ohm. All these three will be in series. It is preferable to connect bulbs in series or in parallel. So it is preferable to connect bulbs in parallel combination. Calculate the equivalent resistance between A and B. So you can see 5 and 15 are in series, 10 and 20 are in series, or else we can say 5 and 10 are in parallel, 15 and 20 are in parallel. So using this, we can find the equivalent resistance between A and B. Now in a which circuit the total resistance is greater than the largest resistance in the circuit? So it is in series combination. The batteries are generally connected in series so that we can increase the resistance value. If two bulbs are connected in parallel and one bulb blows out, what happens to the other bulb? So as they are connected in parallel, the path of current across these two bulbs is different. So if one bulb blows out, the other bulb continues to glow with the same brightness. So here are some frequently asked questions. Derive expression for effective resistance in series combination of resistors. Derive expression for effective resistance in parallel combination of resistors. So with this we are concluding. Thank you so much for attending the class.